So, we just finished, if you're coming from 9.4 where we talked about the tangent ratios, we're talking about two other ratios which describes the different pairs of ratios in a right triangle. So, if you recall, the tangent of a certain angle, we'll call it angle x, was equal to its opposite side opposite from that angle divided by the side adjacent. Okay. Now there are two different pairs of ratios that we could describe. So if we look back down here in this triangle, the right triangle, remember that A to B is always your hypotenuse. The side opposite from the right angle is your hypotenuse. So relative to angle A, this side right here, AC, would be your adjacent side. And relative to opposite side would be BC. Now, we could compare the side lengths. There are two different ratios. So the tangent describes the ratio between this side length and this side length, specifically in the order of opposite divided by adjacent. Now, the thing is, I could find the ratio between the opposite to A and the hypotenuse, or I can find the ratio of the hypotenuse and the adjacent side. So there's two different ratios of side lengths, and that's what we're going to be looking at today. So first one that we want to talk about is the sine function. So that's S-I-N-E, and it's abbreviated with S-I-N. So sine of angle A, for example, the ratio for sine is the opposite side. So opposite side of angle A, so we'll say of angle A, divided by the adjacent, divided by the hypotenuse. So the thing about the hypotenuse, again, the hypotenuse is consistent. It doesn't matter if you're looking at it from a perspective of angle B or angle A, the hypotenuse is always the same. So sine of angle A is equal to the opposite side of angle A divided by the hypotenuse. And then next is the cosine function. So there's sine and now there's cosine, and this is abbreviated with cosine, C-O-S, so cos. So cosine of A is equal to the adjacent side. So the adjacent side of angle A divided by the hypotenuse. So in this case right here, for the opposite side of angle A, this is BC, and the hypotenuse is AB. And cosine of angle A, the adjacent side is AC, and again the hypotenuse is AB. So that is how you describe the other two ratios, with sine and cosine. And again, it will vary if you're looking at it from the angle, the other acute angle, angle B. So let's analyze the sine functions here, okay? So in this example right here, find sine of S, sine of R, and find cosine of S and cosine of R. Okay, so let's look at angle S first. And let's just find sine of S and cosine of S first. So the sine, just to remind us, the sine is the opposite side divided by the hypotenuse. So opposite to angle S is 63. Divided by the hypotenuse, and the hypotenuse is 65, which is opposite to the right angle, so 65. And if you use a calculator, this is equivalent to 0.9092. Now, cosine of angle S is the adjacent side divided by the hypotenuse. So the adjacent side here is 16. And the hypotenuse is still 65. And if you punch this into a calculator, you should get something like 0.2462. So that is for angle S. Now let's look at angle R. So let's find the ratio for sine of R and cosine of R. So sine, again, is the opposite over the hypotenuse. So opposite to R is 16 over the hypotenuse, which is 65. And cosine is the adjacent side over the hypotenuse, and the adjacent side to angle R is 63, and then this is over 65. So sine of R would be equal to 0.2462, and cosine of R would be equal to 0.9692. So again, if you remember from the tangent functions, remember that the tangent of one acute angle was the reciprocal of the tangent of the other angle. So that's the same here. So notice that sine of S and sine of R are reciprocals, and cosine of S and cosine of R are also reciprocals, which means that sine of S is equal, so sine of S is equal to cosine of R, and cosine of S is equal to the sine of R. Okay? Okay. So here's some extra practice problems for us right here. Let's look at number 3. I want to cover this one because it has radicals here. So we want to find sine of f, sine of g, cosine f, cosine g. So let's look at angle g first. So sine of g, and then let's find cosine of g. So sine of g is opposite over the hypotenuse. So square root of 2 divided by 2. And cosine would be square root of 2, which is the adjacent side. So cosine, or adjacent side to g, is square root of 2. And then hypotenuse is 2. So you see how they're the same. And then sine of f and sine of g. So notice how these are the same value. That's because the legs are the same. So we should expect the same thing from sine of f. If we find sine of f, we'll find sine of g. So sine of f would be square root of 2 divided by the hypotenuse. And then that also means that sine of g is going to be the exact same thing. So again, notice that all these are the same, and it's just because the side lengths are the same. And if the side lengths are the same, if you guys remember from what we learned in 9.2, if these side lengths are the same, if they have the ratio of 1 to 1, then that means that these angles right here have to be 45-degree angles. So, okay, so make sure you go through 1 and 2 and find those ratios. Alright, now in this property right here, we're going to take into account what we basically just have noticed up here, and that is that sine of A is equal to the cosine of the other one, so or sine of S is equal to cosine of R, and cosine of S is equal to sine of R. And the reason why this is that these are complementary. So R and S are complementary. So that's pretty much all this complementary angles property pretty much says. So the sine of an acute angle is equal to the cosine of its complement, right? So notice that, so again, that's what I basically just described. So complement, just to remind ourselves, so complementary means two angles. So the sum of two angles is 90 degrees. And the acute angles in a right triangle are complementary. So what this means is that sine of an angle A, so given that we have a right triangle and A and B are the acute angles, that means they're complementary. So sine of A is equal to cosine of 90 degrees minus A, which would be equal to cosine of B. And cosine of A would be equal to sine of 90 degrees minus A, which would be equal to sine of B. Sine of angle B would be equal to cosine of 90 degrees minus B, which would be equal to sine of A, and cosine of B would be equal to sine of 90 minus B, which would be equal to the sine of A. And in this one right here, this is cosine of A. So again, cosine of B is equal to cosine of A because these angles are complementary. Cosine of B is equal to sine of A, and so that's just how it goes. So that's just what we've been stating right here. So that's why cosine of S and cosine of R are equivalent, is because their angles are complementary. Okay. So in this example right here, we want to rewrite a trigonometric expression. So just keep these in mind right here. These are what you're going to want to use. These I guess conversion. You can call these conversion equations. So we want to write sine of 56 in terms of cosine. So sine of 56. So like imagine you have a right triangle. Okay, here's a right triangle. Let's say that this is equal to 56, right? So if we were to write this in one of these conversions, so if we want to write sine of 56 but in terms of cosine, this would be equal to cosine of 90 degrees minus 56. So if you do that, you get this is equal to cosine of 34, which makes sense, right? Because let's say that this side is your opposite, this side is your adjacent to 56. Now again, so sine of 56 would be equal to opposite over adjacent, right? And then we know by the triangle sum property that this angle has to be 34 degrees. Okay. Now, if we look at this angle right here, cosine of 34, if we look at cosine of 34 relative to cosine of 34, this side is opposite and this side is adjacent. Also, I totally misspoke right here. This should be opposite over the hypotenuse. Okay. Also, I should leave these as they were. Sorry. So opposite, adjacent. Okay. And cosine of 34 would be, again, so cosine, if we're looking at this angle, the adjacent side here would be this side length right here. And the hypotenuse would be h. So notice here that they're the same thing. So sine of 56 and cosine of 34 are the same thing. Okay, so that's pretty much all we're trying to achieve here. It's just noticing how they are the same thing. Okay, so go through these examples right here and just use the conversion. I can do one of each, but so we want to write these expressions of sine into terms of cosine. So sine of 9 would be equal to cosine of 90 minus 9, which would be equal to cosine of 81. Okay, and that's really all it is to it. Okay, so that's for cosine. And then here for number 7, cosine of 15 would be equal, in terms of sine, would be sine of 90 minus 15, and this would be equal to 75, sine of 75. Okay, so go through these ones and do the exact same thing, but I'm going to keep going. So here is finding the side length. Now we did something like this similar with the tangent function. So find the values of x and y here using sine and cosine. So we're given this angle right here, so we're going to use that angle for our trigonometric functions. So let's do sine of 26. Now finding the ratio for sine of 26 means I'm finding the opposite side over the hypotenuse. So opposite to this angle is x, and the hypotenuse is 14. So notice how I have this equation now of x with an unknown variable. So I'm going to write this as sine of 26 over 1. I can cross multiply, so I get 14 times sine of 26. Remember that we're not multiplying the 14 and the 26 together. You can't do that. And this would be equal to x times by 1. So you see there that we just get x is equal to 14 sine of 26. And going back to using the calculator, notice that two spaces above my 7 button is my sine function, and 2 spaces above my 8 button is my cosine function. So I want to do 14 times by the sine of 26, and I get 6.1. Okay. Now I still want to find y, so I can use my cosine ratio to find that one. So cosine of 26 would be equal to the adjacent side, so adjacent to 26 is y, divided by 14. So here, if you want to set up a cross multiplication, you can. I'm just going to multiply by 14. So I get y is equal to 14 times by cosine of 26. So 14 times by cosine of 26, and I get 12.6. Okay, that's really all there is to it. So we know x and y values right there. Okay. So I know I have these a little bit out of order, but that's okay. So we're going to be using our special triangles that we learned from 9.3. So we want to find the sine and cosine of angle 30. So angle 30 with a right triangle with a degree of 30, with an angle of 30 degrees, if we draw that out, so let's make this 30 degrees. So if this is 30 and this is 90, then this has to be 60 degrees. Now if you remember the ratios, so the thing about these, so finding the sine, cosine, and tangent of special triangles is that no matter the side length here, so no matter the size of these triangles, every 30, 60, 90 triangle shares the same sine and cosine and tangent ratio. It will always be the same. So if you remember the ratio for sine of 30, for 30, 60, 90, remember that we referred to this side over here as x, and we referred to the longest side as double the side of the shortest side, and this side as x times the square root of 3. So the thing about this is that we can just drop the variables, okay? We're going to drop the variables because when we're talking about ratios, the variables are irrelevant, okay? The ratios is what we're trying to find here. So I'm just going to say that the opposite side to 30 is 1, and the adjacent side to 30 is square root of 3, and the hypotenuse is 2. So by doing this, I want to find the sine of angle 30 here. And sine is equal to the opposite side over the hypotenuse, and opposite to 30 is 1, and the hypotenuse is 2. Okay? Now, cosine of angle 30 is equal to the adjacent side over the hypotenuse, and adjacent to 30 degrees is the square root of 3, and the hypotenuse is 2. So these are the ratios. So I want to do an example though, one more example of a 30, 60, 90 triangle to kind of talk about what I was saying earlier. So let's say that I have another 30, 60, 90 triangle. Okay? But instead of saying that these are the side lengths, let's say I have a side length of 5. Now, knowing what we know from 9.3, this side length would have to be 10, and this side length would have to be 5 times the square root of 3. So if I ask you to find the sine of angle 30, this would be equal to 5 over 10. But this ratio just reduces to be 1/2, right? And then cosine of 30 degrees would be 5 square root of 3 divided by 10. But this would just reduce, the 5 and the 10 would reduce to square root of 3 divided by 2. So you see that doesn't matter the side lengths for these special type of triangles, because the ratios are always going to be the same. The ratios are always the same. Okay, so it's the same thing for a 45-degree angle triangle. So let's draw 45, 45, 90. So the ratio for 45, 45, 90, so if this is 45 and this is 45, so the side lengths here were the same. The side lengths of the legs were always the same. So we can just state them as a ratio of 1 to 1. They have the same side lengths. So we're just going to write them as a 1 to 1 ratio. And the hypotenuse had the distance of, it was square root of 2 times larger than the leg. So 1 times the square root of 2, but we're just going to leave it at square root of 2. So if I'm looking to find the sine of angle 45 degrees, so the thing is, it doesn't matter which one we're using because they're both 45 and they both have the same opposite and adjacent sides. So sine of 45, which would be the same as cosine of 45. It doesn't matter because the legs are the same. And this would be equal to, so you could do, let's say if we're using this angle, the opposite of this angle would be 1, and then the hypotenuse would be square root of 2, and then we just need to simplify by multiplying top and bottom by the square root of 2, so I get the square root of 2 divided by 2. And that's all you got to do there. Okay, now use a special right triangle to find tangent of 60 degrees. So again, if we have the special triangle, let's say that this is 60 degrees, that means this one has to be 30 degrees. Now, opposite to angle 30 has to be the shortest side length, and that we're just going to give it as the ratio of 1 to 2. So the ratio of the opposite side of 30 and the hypotenuse is always 1 to 2, and then that means this side is square root of 3 times larger than the shortest side, so that's how you get those. Now, if I'm using sine of 60, so the opposite side to 60 is square root of 3, and the hypotenuse is 2, so that would be sine of 60. And cosine of 60, so the adjacent side to 60 is 1, and the hypotenuse is 2. So there you go. Okay, now there are some more examples here. This is just using sine and cosine to find the missing variable, which is what we did right here. So you can use this example to model it and use it to find your missing side lengths here using sine and cosine ratios. Okay. All right. So that should wrap it up for us.